you all in this course of electronics engineering, and the code of the subject is KOE038. Today we will discuss unit number 3, and the name of this unit is transistor and its application. So before starting this unit, I would like to explain what we have discussed in the unit number 1 and unit number 2. In the unit number 1 and unit number 2, we have discussed PN, junction, diode, and diode application. So in the first unit, we have focused on the energy band concept. After that, we have seen how the PN junction is formed whenever P-type semiconductor material is joined with the N-type semiconductor. And then we have focused on the application of the diode. And we have seen the main application of diode is rectification. That means incoming AC can be converted into pulsating DC. So the main application of the diode is rectification. And in the rectification process, incoming AC can be converted into pulsating DC, and after some other component, you can obtain the constant DC. And we have seen some other applications such as clipper and clamper and peak detector. So there are various applications of diode. With the help of diode, what we can do, we can rectify the signal. Is that clear? That means AC signal can be converted into pulsating DC. We can clip the signal. That means specific portion of the waveform can be deleted, and we can also perform the clamping operation. That means waveform can be shifted in positive direction as well as in negative direction for the particular application of circuit. And also there is a peak detector, which can be designed with the help of diode for measuring the maximum temperature as well as the minimum temperature, or you can say the maximum voltage, or you can say the maximum negative voltage. So these are the applications of diode in which diode can be used. But there are some limitations associated with the diode. With the help of diode, we are not able to amplify the signal. So if your input signal strength is weak, we are not able to amplify the signal with the help of diode. That means we are not able to increase the strength of the signal if the signal is weak. Because if we discuss about the measurement process, if our instrument is not able to detect the signal, we are not able to perform the experimental procedure. So in some cases, we have to amplify the signal strength, and for that purpose, we are not able to use the diode. So what we can do, we can use another active device, and that device name is transistor. Is that clear? So in this unit, we will focus on the transistor, how the transistor is used as an amplifier, or you can say what are the various applications of the transistor. And we will start with our today's lecture with the name of topics which we are going to cover in this unit. So the first topic which we cover is BJT. So in this unit, this is the first topic which we will cover in this unit. We will focus how the BJT can be fabricated with the help of P-type or N-type semiconductor material. After that, we will discuss the application of BJT, and then we will focus on the different configuration of BJT. And after that, we will focus on FET. So as far as this unit is concerned, we will focus on only two topics. The first one is the BJT and related application. After that, we will discuss about the field effect transistor and the related application in different area. If we discuss about the BJT, we will focus on two types of transistor, NPN and PNP. If we discuss about the FET, we will discuss about JFET and MOSFET, where JFET stands for the junction field effect transistor and MOSFET stands for the metal oxide semiconductor field effect transistor. And depending upon the channel has been formed, further we can classify the JFET in N channel and P channel. Similarly, MOSFET can also classify as D MOSFET and E MOSFET, where D is the depletion type MOSFET and E is the enhancement type MOSFET. Again, you can classify D MOSFET and E MOSFET depending upon the channel is being formed. Is that clear? So further we are having a N channel and P channel D MOSFET and N channel E MOSFET as well as P channel E MOSFET. So we will start this unit basic topic, and the topic name is BJT. So we will start with introduction of BJT. BJT stands for the bipolar junction transistor. Why it is called so bipolar junction transistor, we will discuss. Bipolar junction transistor. So we will start with introduction of BJT. So I have already explained, with the help of diode, we are not able to amplify the signal. So we have to design a new active component or new active device which is used for the amplification purpose. That means we are able to increase the signal strength if the signal strength is weak. So with the main application of the BJT is amplification. So we will start with the introduction. Is that clear? As far as BJT is concerned, there are 3 terminals. So in the BJT, that means bipolar junction transistor, we are having 3 terminals. The first terminal is defined as emitter, that means E. The second terminal is defined as a base, that means B. And the third terminal is defined as collector, that means C. So in the transistor, we are having 3 terminals. The first terminal is emitter, second terminal is base, and the third terminal is collector. Out of these terminals, your base is your controlling terminal. Is that clear? That means output current. What amount of output current we are able to obtain at the collector terminal, it is determined or depending upon the base. How it is related, we will discuss after some time. So as far as BJT concerned, in the BJT we are having 3 terminals. The first one is emitter, second one is your base, and the third one is your collector. Is that clear? Now we will discuss about the BJT. In BJT, current conduction is possible due to electrons as well as holes. So in the BJT, that means bipolar junction transistor, the current conduction is basically due to the electrons as well as holes. That means for the current, if the current is flowing in the transistor, you can say the current is constituted to the device through the minority charge carriers as well as the minority charge carriers. So in the transistor, we are having both types of charge carriers, and current is constituted due to the both type of charge carriers. This is the region. This is defined as a bipolar. That means there are 2 types of charge carriers, minority charge carriers as well as minority charge carriers. Bipolar junction transistor. Is that clear? Now the question arises, why we are using such a specific word, transistor? So we'll discuss about the transistor. It is simply, you can say, it is a combination of 2 words, transfer plus resistor. Is that clear? That means the input current is going to be transferred from low resistance to the high resistance. I am again repeating, the input current in the bipolar junction transistor is going to be transferred, or you can say flow, from low resistance to the high resistance. That is the reason we are using such a specific word, transistor. Transfer plus resistor. Is that clear? So why it is called so bipolar junction transistor? This is very important. Now we will discuss about the types of BJT. That means types of transistor. Types of BJT, that means transistor. In general, there are two types of transistor. The first type is NPN and the second type is PNP. Is that clear? So the first type is NPN and the second type is PNP, and we will discuss about the popularity of this transistor. NPN is more popular. NPN is more popular. Why this transistor is more popular compared to the PNP transistor? Because it is well known to all of us, the mobility of electron is much higher compared to the hole. If the mobility of electron is mu n and the mobility of holes is mu p, you can write the relationship between the mu n and mu p as mu n is equal to 2.5 times mu p. So as you can see, the mobility of electron is approximately 2.5 times compared to the mobility of holes. So electron mobility is much higher compared to the hole mobility. And if we discuss about the NPN transistor, majority charge carriers in NPN transistor are electrons and the majority charge carriers in PNP transistor are holes. So here we are using holes as a majority charge carriers, but here in the case of NPN we are having electron as a majority charge carriers, and the mobility of the electron is higher compared to the hole. So we can say the NPN transistor is more popular compared to the PNP transistor. Now we will discuss about the symbol of NPN and PNP transistor. Now we will discuss about the symbol of NPN and PNP transistor. We will start with NPN transistor. So how we can draw the symbol of NPN transistor? As we are aware, in the transistor we are having three terminals: emitter, base and collector. As the name implies, emitter is used to emit the charge carriers. As the name implies, collector is used to collect the charge carriers. And base is the base of operation. That means base is the controlling terminal. So if you want to draw the symbol of NPN transistor, this is the symbol of NPN transistor. This is your base terminal. This is your collector terminal, and here we are having emitter terminal. Is that clear? So C is basically collector, E is basically emitter, and B is basically base. Is that clear? Now this arrow is basically used to indicate the conventional movement of current. Is that clear? This basically arrow is used to indicate the flow of conventional current through the transistor. The current direction is always indicated with the help of emitter terminal. So this point is very important. You should always keep in your mind the current direction is always indicated through the terminal E. So add the name NPN. How we can retain this basically our point in our mind, how we can draw the symbol. The direction of the arrow is outside or inside. It is very simple. NPN, that means not pointing in. On the other side, we will discuss about the PNP. this is base, collector and emitter. This is the symbol of PNP transistor. Is that clear? How we can, the arrow is basically inside. Is that clear? Pointing inside, PN, pointing inside. So basically how we can retain the symbol in our mind is very simple. Not pointing in and this is pointing in. Is that clear? So basically with the help of symbol we can define whether the given transistor is NPN or PNP. Now we will discuss about the construction of BJT. Construction of BJT. Is that clear? We will start with NPN because NPN transistor is more popular. As you can see here, how we can construct the NPN transistor by putting thin slide of P type semiconductor material. How we can form the NPN transistor by sandwiching P type of semiconductor slides. This must be thin between two opposite type of semiconductor material, that means between n-type semiconductor material, can be formed by sandwiching thin slice of P-type material between two n-type semiconductor material. Is that clear? And the same concept can be used for the PNP transistor, in which we will discuss about the PNP n-type semiconductor slice, which must be thin. We can sandwich between two opposite type of semiconductor, that means P-type semiconductor. Now here we will discuss some property related to transistor. So we'll discuss about the NPN, how they can form it. This is N, this is P and this is N. This terminal is emitter, this terminal is base, and this terminal is defined as a collector. So this is basically NPN transistor. So here this region is defined as emitter, this region is defined as base, and this region is defined as collector. Is that clear? So with the help of diagram, as you can see, the area, if anybody asks you about the area of collector is larger compared to the emitter as well as base. Although it looks like the emitter area and the collector area are same, but more precisely the collector area is larger compared to the emitter area. Is that clear? Why is it so? Because the collector, as the name implies, it has to collect the charge carriers. So the area of the collector must be high. Is that clear? And the area of emitter is less than collector, and the area of the base is very less. Now we will discuss about, so we have seen about the area. Now we will discuss about the doping. The doping of the base must be thin. The base region must be thin and the doping in this region must be light. Is that clear? So for the base region, doping is very less. Why the doping is less? Why the base region must be thin? We will discuss when I will explain you the transistor operation. And the doping of the emitter must be high compared to the collector. So this is very important point. Doping of emitter must be high compared to collector. Is that clear? The doping of the emitter region must be high compared to the collector region. Why is it so? Because as the name implies, emitter has to emit the charge carriers. I am again repeating, emitter stands for, emitter is basically used to emit the charge carriers. So the charge carriers in this region must be high. So the doping of this region must be high compared to the collector. Collector has to collect the charge carriers. So the area related to the collector must be high. Base region must be thin and it is lightly doped. Why is it so? We will discuss after some time. Now we will discuss about the mode of transistor. Or you can say region of operation. So here we will write region, emitter, base, junction, and this is your collector, base, junction, and here we are having application. So basically we'll discuss about the BJT, that means bipolar junction transistor. We are having two junctions. The first junction is defined as a emitter based junction and the second junction is defined as a collector based junction, or you can also define as a base emitter junction, or you can say the base collector junction. Base is always lies in the middle between the two regions, emitter region and the collector region, and it is well known to all of us, base is your controlling terminal. Is that clear? So the first region we will discuss is defined as an active region. Active region. In the active region of transistor, emitter based junction is forward biased and the collector based junction is reverse biased. And we will discuss about the application area. In this region, BJT, or you can say the transistor, used as an amplifier. Is that clear? Amplifier. Is that clear? And the second is cutoff region. In the cutoff region, both the junctions are reverse biased. That means emitter based junction is reverse biased and the collector based junction is also reverse biased. And here this is off. Transistor is off. It is used as an off switch. And the third one is saturation. In the saturation region, emitter based junction is forward biased and the collector based junction is also forward biased. So whenever input side is forward biased, output side is forward biased, that means transistor is on. And transistor is short circuit. This is on. This is on switch. So we will discuss about the active region. In the active region, BJT, or you can say the transistor, can be used as an amplifier. In the cutoff region and saturation region, transistor can be used as a switch. So here in the cutoff region, transistor is off, and here in the saturation region, transistor is on. Is that clear? So in both the region, as you can say, the application for transistor is going to be changed. And also there are third application, transistor can also use as an inverter. So if you will apply 0 input, you can get 1. That means we are applying the 0 volt and we are getting the plus 5 volt at the output terminal. So this is basically application, and transistor can be used as an inverter circuit. Is that clear? Now here, as far as this unit is concerned, we will focus on the two applications, transistor as a switch and transistor as an amplifier. And the question arises how the transistor can be used in the different area by changing the biasing. Is that clear? By changing the operating point. So how we can define the biasing? Biasing is the process in which we are applying the external voltage to the device. Is that clear? And depending upon the type of biasing, we are having 3 regions. The first one is active region, second one is cutoff region, and the third one is saturation region. And now, this is a very important question. An interviewer can ask you, there is a possibility of 4th mode, and that mode is defined as inverse mode. Inverse mode. In the inverse mode, emitter base junction is reverse biased and the collector base junction is forward bias. For the BJT, we will never use such a kind of mode. Why? Because in this mode, collector is behaves like an emitter and emitter is behaves like collector. But at the time of manufacturing, we have designed transistor in such a manner the doping of the emitter terminal is high compared to the doping of the collector terminal. So emitter always has to be emit the charge carriers. But now here collector is basically used as an emitter and emitter is used as a collector. So somewhere the gain of the device is going to be decreased. So this mode of operation we will never use. This is the fourth mode of operation. Now, we will discuss about transistor action, or you can say transistor operation. Transistor operation in active region, or you can say transistor action. So for that purpose, firstly I want to draw the diagram. So as you can see, this is the construction of NPN transistor. We have start the working of NPN transistor. Is that clear? Now this region is basically defined as emitter. This region is defined as base, and that region is known as collector. Now it is well known to all of us, in the emitter region, the majority charge carriers, as the emitter is n-type, the majority charge carriers are electrons. And this is also an region, electrons. And the P region, we are having holes. But as I have already told you, the doping of the base region is very less. So there are only fewer number of holes which are present in the base region. Is that clear? Now, we will discuss about the transistor operation. Firstly, you have to make transistor activate. And how we can activate the transistor? With the help of active region. That means emitter base junction is forward bias and the collector base junction is reverse bias. So this is our transistor action. Is that clear? Now look at here. Emitter base. This is your emitter base junction. This is your emitter base junction, and this is your emitter base junction, and here this is your collector base junction. So this is your emitter base junction and this is your collector base junction. Is that clear? And we have to apply the voltage at the emitter terminal with respect to the base terminal, and also you have to apply the voltage at the collector terminal with respect to the base terminal. So there are two junctions as far as BJT is concerned. The first junction is defined as a emitter base junction and the second junction is defined as a collector base junction. So if you want to operate transistor in active region, emitter base junction must be forward biased. If you want to operate transistor in active region, that means collector base junction must be reverse biased. And also, if you are not able to retain this concept in your mind, there is a very simple way is basically collector has to collect the charge carriers. So the collector terminal has to be attract the electrons of the emitter. So for that purpose, how the attraction is possible at the collector terminal. If you want to attract the electron of the emitter towards this terminal, you have to apply a positive voltage at the collector terminal. If you want your emitted electron must travel or transported towards the collector terminal, definitely you have to apply a negative voltage at the emitter terminal. Otherwise, you should always keep in your mind, for the active region of operation, your emitter base junction must be forward biased and your collector base junction must be reverse biased. Is that clear? So now here we have to apply forward bias voltage to the emitter base junction. So this is N region and we want to make it forward biased. So N must be negative. Here we are having the resistance Re minus plus VEE, and the collector base junction must be reverse biased. So this must be forward biased and this must be reverse biased. And if you want to make it reverse bias, that means N side must be positive. So as you can see, this is the biasing of transistor for the active region. Emitter base junction is forward bias and the collector base junction is reverse bias. Now we will start the working of this transistor. Is that clear? Re and Rc is basically current limiting resistor. Now, if we will apply a forward bias voltage, that means negative voltage at the emitter terminal is base with respect to the base terminal, what is going to happen? These electrons, which are the majority charge carriers in the emitter region, these electrons are going to repel and they are moving towards the base. Is that clear? That region is basically here is defined as a depletion region. We have already understood the concept of depletion region. As soon as PN junction is formed, definitely there is a depletion region. This is also PN junction, depletion region is formed. Is that clear? So as soon as you will apply a forward bias voltage, electrons which are majority charge carriers in the emitter region, they are going to repel from this negative voltage and they are moving towards the base terminal. Is that clear? They are moving towards the base terminal. Now here in this region, as it is well known to all of us, base region is thin and it is lightly doped. So the number of majority charge carriers which are holes are very less. So few electrons which are transported into the base region from emitter terminal, these electrons are going to recombine over here. Only few number of electrons, you can say only 2% of the majority charge carriers which are electron get injected from emitter to base are going to recombine with the hole, and the remaining number of electrons get attracted by this collector terminal. So if there are 100 electrons which you will transfer from emitter to the base and towards the collector terminal, only 2 electrons are going to be recombined into the base region. So if you will transfer 100 electrons, you can say we are able to receive all these 100 electrons at the collector terminal. This is a very simple concept. So if this is the direction of electron, if electrons are flowing in this direction, in the opposite direction there is a current, and that current is known as IE, and IE is basically defined as the emitter current. And if this is the flow of electron, here the current which is flowing to the collector terminal, this is the direction of collector current, and that current is known as a IC. So IC is defined as a collector current. IE is defined as emitter current. Now, few of electrons definitely are going to diffuse through this positive terminal. Few number of electrons are get attracted by this positive terminal. If this is the direction of electron, definitely the direction of the base current is defined as such, IB. So in the transistor, we are having 3 current. The first current is IE, emitter current. The second main current is collector current, IC, and the third main current is IB. And that current is known as a base current. Is that clear? There is a very simple concept. So you have to apply a forward bias voltage. for the forward bias voltage, electrons are going to repel from the negative terminal and get attracted by the positive terminal. So here you can see IE is approximately IC. If we are assuming the charge carriers which are flowing to the positive terminal are very less, so the base current is 0. If we are able to neglect the base current, IC is approximately equal to IE. Now, in place of forward bias voltage, if this voltage is reverse biased, that means emitter base junction is reverse biased, collector base junction is also reverse biased, entire transistor is open circuit, this region of operation is defined as a cut off. Entire transistor is off. Now, if this is forward biased, that means emitter base junction is forward biased, collector base junction is also forward biased. If both the junction, emitter base and collector base junction, both the junction are forward biased, this is defined as a saturation region and entire circuit is short circuit. Entire transistor is short circuit because this is forward bias, this is forward bias, entire circuit is short circuit. Transistor is short circuit and this is defined as a saturation region, transistor is on. So whenever you want to use transistor as a switch, we have to operate the transistor in cutoff region as well as in saturation region. But in the active region, transistor is always used as an amplifier. Now, if we will write the current relationship between, as you can see, if we will apply the KCL, Kirchhoff current law, look at here, sum of incoming current is always equal to the sum of outgoing current. So here, as you can see, incoming current IC, IB is also incoming current and IE is outgoing current. Is that clear? This is the direction. So if you want to write the equation with the help of KCL for the given NPN transistor, from the circuit, we can write IE is equal to IB plus IC. So the emitter current is the sum of base current and the collector current. So IE is basically emitter current, IB base current, and IC is your collector current. Is that clear? So I is equal to IB plus IC, but the base current, the magnitude of the base current is very small, so you can say I is equal to IC. So for the given transistor operation or for the given transistor action, you can define IC is equal to IE. And this is your ideal case. This is for ideal transistor. This is for ideal transistor. IC is equal to IE. But if IC is not equal to IE, this is from basically circuit operation. The previous equation IE is equal to IB plus IC, it is just KCL. But as far as circuit operation is concerned, IC, if it is not equal to IE, IC is equal to alpha time IE, where alpha is your current gain. It is constant for any given transistor. Or you can say the alpha is defined as a current amplification factor. Current amplification factor. So if we consider ideal transistor, if we will consider ideal transistor, in such case alpha is equal to 1. That means IC is equal to IE for ideal transistor. But if alpha is not equal to 1, IC is equal to alpha time IE, and here alpha, the value of alpha is lying between in the range of 0.95 to 0.99. And the value of alpha is basically depending upon the thickness of the base region. If you will increase the thickness of the base region, more charge carriers which was injected from the emitter terminal are going to recombine in the base region. So somewhere your current gain is going to be decreased. The number of majority charge carriers which we are able to collect at the collector terminal, these charge carriers are going to be reduced if your base is thick. But if your base is thin, and if you will transfer 100 electrons, we are able to collect all these 100 electrons at the collector terminal. So you can say IC is approximately equal to IE. We can say IC is approximately equal to IE. So here you can define a new concept about the transistor. IC is approximately equal to IE. Now if your input current, that means if I is equal to 1 milliampere, that means IC is also equal to 1 milliampere. If I is equal to 2 milliampere, that means IC is also equal to 2 milliampere. Is that clear to you? So in the active region of operation, you can say IC is always equal to IE. Approximately. Is that clear? So here in the active region, how we can use transistor? Transistor can also used as current controlled current source. So output current is basically depending upon the input current. If input current is 1 milliampere, output current is also 1 milliampere. If the input current is 2 milliampere, that means output current is also 2 milliampere. So here the transistor in the active region is defined as a current controlled current source. So transistor can be used as a constant current source as far as active region is concerned. So it is all about the BJT operation. Is that clear? I hope so. You can understand the concept of basically operation of the transistor. And if you want to define the emitter current with the help of diode, PN junction diode, it is well known to all of us. IE can also written as IEO, e to the power VBE, where VBE is based to emitter voltage drop, eta VT minus 1. Is that clear to you? Thank you.